Duncan McCoy.
Okay.
And he's going to talk about characterizing slopes of torus.
Okay. Well, thank you very much to the organisers for inviting me. It's a pleasure to be here. I have to say the idea of recording lectures is a novelty that, well, the idea that any silly statements I make may be preserved for posterity is helpful, as it really focuses the mind and encourages you to get it right. So, well, I guess we'll start by recalling sort of Dane's surgery. So lots of people have already spoken about this. But when I prepared my talk, I didn't realize so many people have already told you, so I'll recall it anyway, stick to my script. So P over Q surgery on K is, I'll denote it by this, and it's what you get by taking S3, removing a tubular neighborhood of your knot, and then gluing back in another solid torus by some map where this is some map on the boundary where it's all set up so that P times the meridian plus Q times the longitude bounds a disk. And where sort of you want your longitude to be null homologous. So this is motivated lots of questions in low-dimensional topology, sort of questions of the form which three manifolds arise by surgery on S3, and sort of as a secondary question, how unique are these descriptions? When they exist. So I guess it's an old and sort of well-known theorem that every, I guess, three manifolds. So I'm always talking about oriented three manifolds arises by surgery on a link in S3. Also an old result of licorice, but not always on a knot. I guess the crudest obstruction to arising by surgery on a knot is the observation that, well, you've got cyclic first homology if you're surgery on a knot. So, well, today I'm sort of more interested in the second question, in a sense, and sort of, I guess, in line with this question about how unique are surgery descriptions as a definition due to Ni and Zhang, which sort of neatly encapsulates a certain notion of uniqueness and can be used to describe quite a lot of old results in sort of Dane surgery. So a slope P over Q for K is characterizing. well, if the oriented homeomorphism type of P over Q surgery determines K uniquely. So if we have this situation for some K prime, then this implies that K and K prime are in fact the same. And this is oriented homeo. So I guess some examples of this in concept in action or in order. So example, I guess 1. So every slope is characterizing for the unknot. I believe this was originally a conjecture of Cameron, and it was proven by Kronheimer, Mrofka, Osvarth, Weber. More recently, every slope is characterizing for, well, the trefoil, so the T32 torus knot, and for the figure 8. And these two are these 4 names apply to this one, and these 2 names apply to these 2. I guess. And well, more recently, I guess, as I understand it, these are the only 3 knots for which the set of characterizing slopes have been completely determined. As far as, for example, for other knots, it's known that for T52, any non-characterizing slope, so it now becomes easier to describe which ones can be non-characterizing, possibly non-characterizing rather than the ones which are characterizing. Any non-characterizing is either a negative integer or sort of or lies in a finite set of other. I'm doing a very bad job of describing this, a set of other slopes. So, and this is Ni and Zhang in the paper where they sort of introduce this in this terminology. And well, you can produce a few more examples. So, for example, with a little work, you can see that now we're on to TRS. I mean, as the title sort of gave away, I'm mostly interested in torus knots today. So for TRS, say RS plus or minus 1 over Q is characterizing for Q greater than or equal to 2. This follows from the cyclic surgery theorem, which is and well, we're on to the final set of examples, I promise. So again for TRS, any okay, and from now on, I'm going to want R and S greater than positive. I mean, you can obtain similar results by reflecting your torus knot, and it's not hard. So I'm going to save myself chalk and let you do it. Any any slope V over Q is characterizing, and this is again yin zhang, and I guess I should sort of plug that actually you can show NSS will do. So this was something I did in my thesis. So you can push this down to something which is linear in RNS. So those are some examples. How about some non-examples? So, well, some of these examples will possibly indicate why I'm sort of talking about torus knots, because it turns out you can prove things about characterizing slopes for torus knots, whereas life in general seems a little less pleasant. So, having said that, I guess the first example everyone always seems to give of these things is actually a torus knot example. So T11.2, this is a lens-based surgery, and it turns out to be the same lens-based surgery as T54. And this is an example showing why I had to have Q greater or equal to 2 here, because life becomes false when you let Q equals 1 in there. And there's another set of more interesting examples that are a family of examples due to Baker and Motegi. So there exist knots for which every integer slope is non-characterizing, and I guess there's quite a nice bit of nice picture that can go with this. So the starting point for some of these things is to start with a link with a two-component link with an unknotted component. So that 0, 0 surgery on both of these returns back S3. So then the observation is that, well, since this is a surgery diagram for S3, if I put zeros on this, then you've got a knot, say, K here. And if I do, say, N surgery on this, you can do a little slam dunk move. To get, well, minus 1 over N surgery on here, still 0 surgery on here, and then you can do a twist on this to get N twists here. I guess if you call this Kn, this construction produces for you a family Kn such that this is true for all n, and if you sort of choose these examples carefully, you get infinitely many distinct knots. And are they? Presumably they're all in. It's the condition that as long as you're not a meridian, these sort of give you. Yeah. So as long as you don't do something silly, this gives you an infinite family. But if you do something particularly nice, you get distinct ones for every n. And these examples are such that, which will be useful later, the degree of the Alexander polynomial tends to infinity.
Sorry. Do you have two strands coming into the zero frame done knot, or do you have more?
Where n is equal to 2. So an arbitrary number. It's just, I just happened to draw 2 because I didn't want to draw 1. Yeah, so this is just some, this is not, this is some random junk, and the property is that you want zero surgery on both to give you back S3. That seems to be the only criteria. So, and the final set of examples is again a torus, family of torus knot examples, and I'm finally getting to the point, so be patient. My final set of examples are for the torus knot with the following properties. So for r s greater than r greater than 1, and q greater than or equal to 2, we can construct an example when r greater than q so when q is equal to this, when these formulae are satisfied, we have this then so for R and S, such that we can take q equals to this, and all these things are integers. The punchline is then the cable of a torus knot table of torus knot K such that it's an example of a non-integer, non-characterizing slope for a torus knot.
So why is S
It's not. So part of this condition is implicitly these conditions are implicitly the conditions are requiring both of these quantities to be integers. And I guess the other remark is as I've set it up, it's sort of clear that for a given torus knot, there is at most one such slope. Q Q is determined by R and S, and P is then determined by Q and R. So there we have some examples of non-integer slopes and non-integer, non-characterizing slopes for torus knots. And, well, I'm going to sort of make the following sort of claim, conjecture. You know, these examples are the only non-integer, non-characterizing slopes for torus knots. And, well, I guess I should have some evidence to back up this claim, and my evidence to back up this sort of, you know, evidence for this conjecture is, well, to sort of wave my hands and point you to a bigger conjecture. So the conjecture is that if surgery on a knot gives you a Seifert fibered space, and Q is greater than or equal to 2, then K is a torus knot, or a cable of a torus knot, so, well, my evidence is that this bigger conjecture that cleverer people than me have made implies this smaller conjecture. And I guess if this formulation, the conjecture, maybe looks slightly strange, you might have seen it in a slightly different form, which is that if K is hyperbolic, and is Seifert fibered, then and these two guys are equivalent. So I guess the implication in one direction is clear, since neither of these two things are hyperbolic. The implication this way is more or less straightforward, and the implication in the other direction sort of follows from work of Gabay on knots in solid tori, giving back solid tori, which I will return to in a second. And, well, I guess the implication here is sort of coming from the observation of Moser that surgery on torus knots gives Seifert fiber spaces. Okay, except for the irreducible one. So checking this implication is simply a case of checking when a torus knot and a cable of a torus knot can have the same surgery. And well, the main theorem of this talk is to sort of, for each, verify this conjecture for each torus knot up to a sort of a finite set of possible exceptions. So basically, to put the rest of the torus knots on the same footing as T52. So the sort of the precise statement that I want to discuss is, well, if we have a knot with the same P over Q surgery, it's a non-integer surgery, then, well, if either Q is greater than or equal to 9, or P is sufficiently large, then, well, where sufficiently large means sufficiently large means this, then, well, either K is TRS, so, or K is cable of torus knot. From the example. And I didn't write it down here, but you can, in each case, there's a single possible candidate for the cable of the torus knot, and you can write down explicitly what it is, but I didn't, and I'm not going to. So you can fix this. And I guess we can have a little schematic of what this theorem says for characterizing slopes. So if I draw a little, if we have Q up here, P up here, what does the theorem say? Well, it says if you're up here, you're a characterizing slope. If you're outside here, you're a characterizing slope. I guess I don't want to touch the axis down here. If you're out here, you're a characterizing slope, with the possible exception of this single slope, which could be non-characterizing. And I guess I should say something about the axes. Well, this axis up here is known to be all characterizing slopes, but sort of, I guess what's going on this negative axis is unknown to me. So how does the proof of this theorem go? Well, the proof follows the same sort of model as the approach used by Ni and Zhang in both of these. You just have to sort of soup up some of the ingredients at various stages. So the proof idea is, well, Thurston tells us that K, so now K is the sort of potential not giving you a non-characterizing slope. Thurston tells us that K is either torus knot, satellite, or hyperbolic. So the proof is to sort of deal with each of these cases in turn. So I'll begin with the easy one, I guess. If K is a torus knot, then, well, you can compute explicitly what the spaces you get are, compare with what the space you get on your torus knot, and, well, what you find is that if K is a torus knot, then there are only two possible slopes for P over Q, and this is one of these examples. Such examples exist, but they're outside the scope of the theorem, so it's fine. So the more interesting case is the other two. So what happens in the other two cases? Well, if K is a satellite, then you look at the incompressible torus, the innermost compressible torus. And the knot complement. So, well, this space is a small Seifert fibered space, or it's a lens space, or it's reducible. But in the cases of interest, it's irreducible, toroidal. So I guess we'll call this innermost incompressible torus, say, T. Compressible torus, we call it T, say. So when you do your Dane surgery, disappear under surgery. So the knot K inside, well, the knot K is inside your solid torus, and, well, Gavai tells us, as John mentioned in his talk yesterday, this means K forms either a zero bridge or a one bridge knot. And, well, it's known what are the surgeries on these guys which return back a solid torus, and this can only happen when Q is equal to 1. So, well, K must take the form of a zero bridge not in T, but that's exactly a cable. So this implies that K is a cable of, well, what's this a cable of? It's a cable of some knot K prime. But we chose this torus T to be innermost, so in particular, this knot K this knot K prime doesn't have any further incompressible tori in its complement, so K prime is either a torus knot or hyperbolic. And well, what happens when you do your surgery and you sort of replace the solid torus inside T by another solid torus? Well, this means that when you calculate sort of how the solid torus is replaced, you end up with, well, I mean, this is well known, the winding number squared of the pops up here. So anyway, the upshot of this is we've shown that if K is a satellite, either it's a cable of a hyperbolic knot, or it's a cable of a torus knot. If it's the torus knot, K prime is torus, then this is kind of what we wanted to check. So, and we can sort of refer to our earlier computation that these are the only such examples we've done. So you need to rule out a hyperbolic case. Fortunately, well, so this is the reason that I sort of discussed the satellite case first, because you can reduce it down to the, it reduces down to the hyperbolic case, so you can talk about those all at once. And well, so we need some tools for ruling out Seifert-fibered surgeries on hyperbolic knots. Fortunately, lots of people have done lots of thinking about this sort of thing. So, well, we can invoke some results on hyperbolic geometry. So, I guess first case is the bound on distances between exceptional surgeries. So I guess this black and B Meyer half, which is that if, say, if M is hyperbolic manifold, that's with a single cusp, then two exceptional fillings with slope alpha and beta satisfy, well, they satisfy distance at most 8. So in particular, well, case of interest, if I have a hyperbolic knot and a a hyperbolic knot in S3, we've already got one exceptional surgery. That's the one giving you back S3, and the distance between that and P over Q is Q. So in the case in question, if we had an exceptional surgery on a hyperbolic knot, this would be at most 8. And as you can see, the number 8 is quite clearly appearing in my theorem, wherever it's gone, as the number 9. So, okay, it's right in front of me. So this 9 here is exactly that theorem there being invoked. So in that picture up there, that's the sort of the big blue region at the top. So we still need something to deal with the two side regions. So for this, I'm going to black box some more geometry. So there's a result from the paper of Yin Zhang using again, well, maybe I'll Lacan B. So this one is a consequence of the 6th theorem. I guess the other people going into this is that if K is, say, any exceptional filling satisfies say P over Q. Well, and this is the mysterious 43 over 4 that I sort of have in my, well, that pops up in there. That's the same 43 over 4. So we want to use this to, well, we want to use this to rule out, for example, this guy being hyperbolic, or just simply K itself being hyperbolic. So to do that, we need to find some upper bounds on the genus of K in terms of so for K, say, we want bounds on GK, and as this is the point at which I have something sort of new to add to the story, and that's via, well, you can obtain such things by the following theorem. So I'll give you the sort of the general, I'll give you the sanitized version first, and then I'll give you the version that I'm actually going to use here. So if we have this, we have this situation, and say, well, Q greater than or equal to 3, and say p greater than or equal to greater than or equal to this quantity here. So if the surgery slope is large relative to both Q in some sense and the genus of one of the knots, then, well, the two knots have the same genus. They have the same Alexander polynomials, and, well, K is fibered if and only if K prime is. So, as I said, this is the sanitized version, because you may be looking at these conditions here, and your spider senses may be tingling, because those are exactly the sort of bits of information you can get out of knot flow homology in a relatively straightforward fashion. So, you know, your spider senses would be right, because that's exactly what's going on. So, if one is prepared to sacrifice the sort of absence of knot flow homology conditions in the statement, then you can say something a little stronger. Well, in particular, this theorem isn't really any good for our purposes, because this is still a little too large, and I don't really want to state theorems about non-half integer and non-integer surgeries. That's a little clumsy. So what's the extra feature we can use to get rid of that? Well, say if K is an L space knot, say we have, again, have the same setup as before, with, in this case, if, well, greater than or equal to the same bound, okay, and now well, either we can have Q greater than or equal to 2, or is an L space, then we get the same conclusions. So, same genus, same Alexander polynomial, and, well, since K is an L space knot, it's fibered, so K prime is fibered. And note that I'm just insisting that K is an L space knot. I'm not insisting that the surgeries in question actually be L space surgeries. So now, when you take this this extra ingredient, well, we know that we have this setup. So under the hypotheses of the theorem, which I've now thoughtlessly erased, we can conclude that these two guys have the same genus, and my whole hypotheses were such that this condition is satisfied, so that tells us that K is not hyperbolic. And now, well, if we look at this again, to sort of finish off the satellite case, we know that these two guys still have the same genus, and K is fibered. So, for example, by looking at the degrees of Alexander polynomials, we can conclude, well, we know that K prime is also fibered, so we can conclude that the genus of K prime is less than the genus of this. Well, in particular, it's still satisfying this, so that's how we rule out that, and sort of that's the completion of the proof. And I guess I should say a few words about sort of the proof of these theorems. Well, the sort of surgery mapping cone formula of Osvath and Szabo give you a recipe for computing the Heygaard-Floer homology of things obtained by surgery on your knot in terms of the knot-Floer homology of the knot you started with. And so you prove this this theorem by slowly working your way through that and unpicking it. And, well, conveniently, I seem to have more or less run out of time. So I'm obliged to, well, I should say a little bit more, but not too much. So one of the key, the first step in implementing the mapping cone formula is to sort of label the spin C structures on the manifold you obtain by surgery. And now we're sort of obtaining the same manifold by surgery on two different knots. So a priori, you may obtain two different labelings, but, well, the D invariants of the manifold you obtain by surgery are basically, up to an integer shift, the D invariants of the corresponding lens space. And the D invariants of lens spaces satisfy lots of nice number theory congruent type properties. So you sort of compare how these two different labelings look next to each other, and it turns out that sort of this condition on P here is sufficient to guarantee that these two labelings are essentially the same. So that's where this condition is coming from. And then you take your two labelings and start comparing sort of each spin C structure in turn. And because we're insisting, well, in this case Q is greater or equal to 3, and here Q is greater or equal to 2, sort of all the reduced terms from the knot-Floer complex pop up, in this case 3 times, and in that case twice, but that's enough for you to look at the two, the absolute gradings on sort of both of, when all the places that these occur, and then when you compare these, you find that these groups must have been living in the same place for both knots, and then that's sufficient information. Unfortunately, well, it might be possible to recover a stronger result saying that they have the same knot-Floer homology in some sense, but I wasn't able to do that. But you can match up enough information that these conclusions drop out. Anyway, thank you for your attention.
Are there any questions for Duncan?
So is it possible to prove such kind of theorem for hyperbolic aerospace?
as in for hyperbolic L space knots.
You have that.
I don't know. I don't know enough hyperbolic geometry to say what you'd be able to do. I mean, in principle, maybe you can just give some geometric control over what the knot looks like, but I don't know.
Well, if there are no more questions, let's thank Duncan again.